All right, continuing with our discussion of geological time principles and the scientists who first laid out these ideas for us, we go back to James Hutton. Now remember, James Hutton, I talked about him in the very beginning of the class as the originator of the whole idea of uniformitarianism. That is, the present is the key to the past. Geologists will look at modern environments and modern animals and modern processes, the modern world, to help them decipher the ancient world in the rocks. Now we're going to look at him a little bit more detail. He is also operating at about the same time, the late 1700s, early 1800s, and he's responsible for a book called Theory of the Earth, in which he recognized what we call today deep time. That instead of counting up the begats of the Bible and somehow coming up with an age of the earth being just a few thousand years, he looked at rocks and ultimately reasoned that to do all of this, you needed millions and perhaps billions of years. So uniformitarianism, but today we're going to talk about his other principle, which is unconformities. So, unconformities are simply the deposition of sediments not being continuous. If you think about the rock record, and a lot of people say this, they use this metaphor, that scientists read the rocks like pages of a book. And if you think about it, if you use Steno's superposition principle, the oldest on the bottom, the youngest on the top, it's like reading a book from pages 1 to, say it ends on 500. But it's never that perfect. Instead of having a book with all pages 1 through 500, it's a book with many, many pages gone. There are gaps. Think about that. If you had to read a book that didn't have all the pages, well, maybe if it had a few pages missing, you could still kind of figure it out. But what if you were missing the 100 pages right in the middle? Or what if you were missing every other page? Or what if you only had page 1, page 50, and page 500? Could you still do something? Well, you could still sort of tell a few characters, a few things going on, location, maybe the time, but not much. And that's more the case with the rock record. So, unconformity is the name we give to the gaps. And the gaps can either be to the sediment never being deposited there, or it was deposited and later moved. And so the analogy to these books that you see over here, you could either have some screw up where the publisher just didn't include pages 50 through 75. So you have a book that never had those pages in it. Or you have a book that some kid or somebody came along and ripped out huge pieces of it all through it. Either way, you are missing pages and missing the rock record. And he came up with several types or flavors of unconformity, places where rock pages are missing. So you need to know the difference between these three. And generally, I always tell people, you need to know these as cartoons on an exam, whereupon I ask you, what is it? What you're looking at. The first of these is the nonconformity. And in a nonconformity, you have sedimentary beds laying exactly on top of igneous rocks. Intrusive igneous rocks, those rocks that are formed well below the surface of the earth. And so you have to imagine this whole area pushed up to the point where these rocks from deep below the earth are exposed. Then they're weathered away. Then the whole area drops down and new rocks are laid on top of it, so that that line, that place where those two rock types meet, has a big gap in the rock record. The picture you're looking at over here is a place out west where there's a gap of about 100 million years. And so you have, if you have flat-lying rocks and you've got igneous on the bottom and younger sediment rocks on the top, that's a nonconformity. The angular unconformities are the ones that are probably most striking, because you look at the rocks and you see this angular relationship between the older rocks, which are tilted, folded, they're altered somehow, and then younger flat rocks or less deformed rocks on top. Right here, you're looking at a picture of the Grand Canyon, and right about where I'm moving the cursor is the site of what's called the Great Unconformity, and we're missing about 1 billion years of time here. Look at the rocks at the bottom, below where those words are, and you see those rocks are kind of coming up at a very slight angle, and then the rocks on top are flat. That gap right there, you have to think what happened here. All these rocks had to have been deposited flat, then they had to be tilted, then they had to be eroded down and new flat stuff put on top. And as I said, in this particular spot, the lack of rock there is about 1 billion years. Hutton is intimately associated with the whole idea of these angular unconformities because this is where he grasped deep time. In Scotland, there's this place called Sycamore Point. It's a famous place. All geologists want to go there. And when Hutton came and saw it, his mind grew giddy. Silly phrasing, but that's the words he used. Contemplating the time it required to make what he saw. So the big block diagram you see over here, it's a cartoon of Sycamore Point. Notice the rocks at the bottom are at a sharp angle. Then there's a line, the unconformity, and then flat rocks laying on top of it. And he did what geologists do. You have to go back in your mind to reassemble the whole thing and imagine what happened. So, at first, these older rocks were deposited flat at the bottom of the ocean. Then, something had to push them up, tilt them away from horizontal, then erode them down, then have the whole thing drop down a new ocean deposit or on top of it with new sediments deposited on it, and then the whole thing uplifted again where we can see it today. And when he looked at this, and this is a famous quote from him, he saw no vestige of a beginning and no prospect of an end. He could imagine geologic time going on for millennia in the past and towards the future, deep time. The next picture is me proudly standing on Sycamore Point in Scotland. I had the good fortune to teach in Scotland in a study abroad program twice in the past. And if we ever get back to doing such things as study abroad, I strongly urge you to consider doing the Wisconsin and Scotland program. Excellent program. You get to see Europe all over, not just Scotland. And if you have a geologic professor, they're going to drag you out here. Notice, right where I'm standing on the line, and the rocks below are vertical, the rocks above are relatively flat. This is Sycamore Point, and right where I'm standing, there's this huge gap. Here I am explaining, going nuts, explaining to several of my students, former geology students that went with us on this trip. We spent the whole semester there, and it's a place that's on every geologist's bucket list, and I'm certainly glad I made it. The third flavor of unconformity is what we call a disconformity, and this one's not as obvious. You don't have a striking igneous to sedimentary or angular rocks to flat rocks relationship. If you're just staring at a cliffside or a quarry wall or something, it's going to look like a stack of flat rocks. But in this diagram, where the wavy thicker line is, and realize they're never always going to be that obvious. Usually you're just going to see stacks of rocks here, but I can tell you that this would represent a gap. It could be a huge gap. If I had a fossil dinosaur bone in this sort of beige colored rock, and then the next one above it had fossil humans, the gap between the last dinosaurs 65 million years ago and some of our earliest ancestors about 2 million years ago, you're looking at 60 plus million years that might be missing here. Notice I said fossils. Disconformities are very, very hard to tell. The only way is typically what fossils are there. So this is the first inkling that we have that fossils may be important for time telling. And that takes us to the last of these heroes for this geologic time lecture, William Smith. Again, late 1700s, early 1800s, and he was a person that his job was to build canals, do engineering, basically move things from one place to another, and he was responsible for digging lots of holes in the ground, and he would note the rocks that he saw there and the layers and the fossils. And he collected fossils all over England, and he recognized that fossils, they've got a unique story. They're not random. They are found in very specific places, and then they're not found there. Oh, incidentally, he also produced the first geologic map, which it's been called the map that changed the world, and we'll talk about that later. But let's go back to fossils. He is responsible for number 7, fossil succession, and this is saying that fossils are not random. They occur in a very particular order, the order that William Smith collected them. Now the cartoon over here sort of shows graphically shows how these fossils may appear. So let's go to the next slide. And you see the fossils down below, A, B, C, D, and E, and you've got some clams, oysters, a nice crab, there's a snail, there's an ammonite. And these letters, A, B, C, D, E, correspond to these lines you see here. Now, if you imagine these were rocks in a quarry or a canal hole that he was building, he would mark where fossils were found. So fossil A he found at the bottom. And then he'd find it, and then at some point in that hole, he would stop finding it. Fossil B would have a different orientation. It would be found a little bit higher, but continue. Fossil D, this snail, the least amount of representation here, but it would be found here, here. And what he found was that this order of things, A comes first, then B and C arrive, then D, then E, then A stops being there, then D stops being there. This pattern is repeatable, meaning he could go to Wales and find it that way. He'd go to England and find it that way. You could look at rocks in Europe and find it that way. Now we know you can go to places, if you're lucky, across the globe. Go to the United States, there's that order. Go to Argentina, there's that order. Australia. Fossils appear and disappear in a regular pattern on planet Earth. Doing this is called biostratigraphy. And the vertical or sort of extent of these fossils, there's plants, misspelled, sorry, but the vertical extent of these rocks, you could take that to be when they lived on planet Earth. So look over here. Here's 3 localities. These could be 3 places in England, or it could be Jefferson County, Wisconsin, Walworth County, Wisconsin, Milwaukee County, Wisconsin. Steno told us that the rocks are oldest at the bottom, youngest at the top, and that they're originally laid down flat. And these little blips, these little beige colored blips here with cute little icons by them, are the ranges of different fossil species. So you would find this one at the bottom, and at some point you stop finding it. Then in the middle you'd find this one and stop finding it, and then this one and stop finding it. And you see there's variation from these 3 localities, these 3 counties in Wisconsin, but the general pattern holds. Rock C, or fossil C, appears first. Fossil A appears after that. Fossil B after that. Knowing this, we have since built up the geologic time scale. So we do this same thing. These 2 pictures are pictures of students in the field going, and what we do is we measure the rocks, we describe them, we note where they are, and we collect fossils, and we'll say, this fossil appears 7 inches above the bottom, and then it stops at 3 feet and 4 inches above the bottom, etc. You can do this anywhere you have sedimentary rocks. And then this data is then composited everywhere. And it has created the geologic time scale, which is geology's greatest contribution to human thought. That time is immense, and because we have organisms that live on planet Earth and die and leave their skeletons there in a particular order, we can tell time and create the geologic time scale.